This is part 8 of the Module 9 lecture. And in this part, we're going to look at an example where we compare the means of two independent populations that have unequal variances. Again, I'm going to illustrate the procedure that we've been using since Module 8 to compare a hypothesis. Here's the example. So the authors of the paper entitled Sex and Salary, a survey of purchasing and supply professionals, conducted a study of female and males who work as purchasing managers. So the yearly salary of a random sample of 45 males and 35 males was obtained. The sample mean and standard deviation of the salary in thousands of dollars of female managers are 64.6 and 8.618. So this is the mean and this is the standard deviation of the salaries of the managers in the sample. Also in the sample of the 45 male managers, the sample mean of their salaries was 74.6 and their standard deviation of 5.397. So a tested hypothesis of the variances has shown that the two populations have unequal variances. So the question is if the average yearly salary of all male purchasing managers is larger than the salary of all female purchasing managers. And we want to compare this using a significance level of 0.05. And then we would like to obtain a 95% confidence interval for the difference of salaries. All right, so now as you can see, these problems start to give you a lot of information. So a good idea is to summarize the information that you're given. So now here we know that we're dealing with two independent populations with unequal variances. Then for the females, you have 35 females with an sample average of 64.6 and a standard deviation of 8.618. Then you have 45 males with a sample mean of 74.6 and a sample standard deviation of 5.397. We want to conduct this test at a significance level of 0.05, and the objective is to determine if the population mean is larger for males than for females. So we're comparing two means. All right, so now with this, then we know that we're dealing with a comparison of two independent populations. They have unequal variances, and we would like to compare the means of these two populations. All right, so with this information, we can start our procedure, and the first thing is to write the hypothesis. So in this case, we want to see if the average salary of males is larger than the average salary of females. That is giving you the alternative hypothesis, and because we're using two means, then we use the difference. So if the average salary of males is larger than that of the females, then that difference should be bigger than 0 because this mean is larger than this mean. Also, and of course, the null hypothesis is that this difference is equal to 0 or less than 0, because then the average of the females is equal to that of the males or larger. All right, looking at the alternative hypothesis, we know we have a right-tail test, and the significance level is given to us as 0.05. In step 2, we select the distribution to use. So here we have two random samples, and then we know that because they are random, the observations within each of the samples are independent. Both sample sizes are larger than 30. One is 35, one is 45. So then we know that the sampling distribution of the first mean and the sampling distribution of the second mean are normal. And if those two are normal, the sampling distribution of the difference of those two will be also normal. Now, the population variances are not equal and are not known, and therefore we estimate them using the sample variances. That all of these three things is telling us that we should be using the t-distribution with the degrees of freedom unequal, because we're dealing with unequal variances. All right, so in the next step, the first thing is to calculate the degrees of freedom of the t-distribution. So we calculate these quantities V for the males and V for the females and here, this is very important. They're giving us the standard deviations, but we need to work with variances. So we squared the standard deviations to get the variances. So this ratio gives you this value, and the ratio for the females gives you this value of 2.122. Now, using these two numbers and incorporating them into the definition of the degrees of freedom and carrying out all these calculations, then you see that this is 35.9075. And again, we're not using software, and I'll just follow the rule that the book gives you, that it says that you always round down the degrees of freedom. And this is because you're making the test more conservative. So you want to be more careful in whether to reject a null hypothesis or not. All right, so we'll follow that rule. When you're dealing with a software package, a statistical software package, this is handled transparently because you can work with fractional degrees of freedom. Right, but remember, the way we're working, always round down the degrees of freedom. Here you will think that this should be 36, but we're always rounding down. All right, so the degrees of freedom for this t-distribution is 35. With this, then we proceed to calculate the test statistic. And so here's the difference of the averages of salary, the sample averages of salaries for males and females. And the difference of the means under the null hypothesis is 0. So that's set to 0. And then we have the variances and the sample size, the ratio of the variances to the sample sizes for both samples. So you plug in the numbers in here, and if you carry out that calculation, the t observed is 6.0092. All right, so if we decided to follow the critical value approach, then the right tail test with the rejection region will be in the upper or in the right tail of the t-distribution. So we go into table 5, we use 35 degrees of freedom, and this is a right tail test, so we use the alpha of 0.05. If you look at your table at the row where you see 35 degrees of freedom and you go across where you see the probability of 0.05, you find that the t-critical is 1.69. Therefore, the rejection region is for whenever the t-observed is larger than 1.69, then you reject the null hypothesis. And you can see here the t-observed is 6.0992, much larger than that. So that's in the rejection region. You can tell right away. All right, so if you decide to follow the p-value approach, then this is the t-observed, 6.0092. Then you go into table 5, look at the row for 35 degrees of freedom, and look at the t-values on that row. And you see that the largest t-value on that row is 3.34, and that corresponds for a probability. If you look at the top, that's a probability of 0.001. And see, the probability that t is bigger than 6.0092 is much smaller than this probability that we find in the table. So that tells you the p-value is between 0 and 0.001. If you like to calculate the exact p-value using the t-distribution, then you see that this thing is, the p-value rather, is 0.000075. Very, very small. All right. And with that information, then we can go on and make a decision about the null hypothesis. And you see the t observed is much larger than the t critical, as we noted earlier. And the p-value is between 0 and 0.001, which is much smaller than 0.05, the significance level. So both of these conditions, either one or both, tell you, and both tell you that the null hypothesis that the two salaries are equal should be rejected, or less than 0 or equal should be rejected. So we can conclude that at that 0.05 significance level, the population mean of the salary of male managers is higher than the population mean of the salaries of female managers, because we're rejecting the null hypothesis, saying that this difference is bigger than 0, implying that the mean of the males is larger than the mean of the females. All right, so this is what we can conclude from the hypothesis test. But again, you may be more interested in finding the actual or estimating the actual difference in salaries. So the the hypothesis test rather does not allow us to tell, doesn't tell us how big that difference is. It simply says the mean of the salary for males is larger than the mean for the salary for females. So we need to go and calculate the confidence interval to determine the magnitude of that difference. So we know we have a confidence level of 0.95 because of 95% confidence interval. Then alpha is 0.05. So to calculate the two limits, we divide alpha by 2, which is 0.025. And we know the degrees of freedom is 35. So if you go to your table and look at the row with 35 degrees of freedom, and you look at the probability of 0.025 from the top, you find that the T alpha over 2 is 2.03. All right, so now we have this T value. We have the difference of the two means. We know the sample means, we know the sample variances and the sample sizes. So if you plug in all those numbers in here, you find that the lower confidence interval is 6.6218 and the upper confidence interval limit is 13.3781. All right, so the difference in salaries, the males versus minus the females, is between 6.6218 and 13.3781 at a 95% confidence level. So because these two numbers are positive, that means that this difference is positive. So the mean of males is larger than the mean of females. That's why the difference is positive. So then we can say that at 95% confidence level, the average salary of all male managers is between 6.62180 and 13,378.10, higher than the mean salary of all female managers. All right, so this is the one example that I have to show you how to compare the two means of two independent populations that have unequal variances. So I'll stop here. In the next module, we'll talk about the next topic in Module 9.